All right, so the first test we're going to do is the sodium test. The sodium test is extremely sensitive. In fact, it's too sensitive. It's too easy to detect sodium ion. And so the problem with sodium is that a lot of people end up getting false positives. You know, they think they have it, but they don't. The reason why they detected the presence of it was because of contamination. And so we have to be careful with the sodium test. Well, what's involved in the sodium test? If you have an unknown solution, that is, we'll call this the unknown, or U and K, and you suspect in this unknown you have sodium ions, then the test is pretty simple. What we'll do is we'll just put some of that solution into the flame, and we end up with a yellow flame. So if we get a yellow flame, then that's a positive test for sodium ions. The problem is like I said, sodium's everywhere. So for example, the way we introduce this solution into the flame is by using a platinum wire, because platinum's very unreactive. Well, the problem is if you touch the wire with your fingers, you're going to test positive for sodium. In fact, everything you touch, you leave a sodium residue. And so if the test for sodium is extremely sensitive, we can't even use glass, because Pyrex glass like this leaches sodium ions out. And so we would use something like polyethylene. Our test isn't that hypersensitive, so we're going to use glass. And so all we do is we get a sample of unknown, for example, DI water. And then dip the wire in to the water, get a little bit of water here, and then see, do I detect the presence of sodium? And so let's do that here. Gotcha, folks. This is the flame test. Oops, vacuum. For sodium. Let's take a look at the flame. The flame, you know, you might want a big flame, but if you have a big flame without much structure, it's not really worth doing here. What you want is you want a decent flame with a nice cone on there. And so it could be a lot smaller flame. As long as you have a nice cone there, temperature should be plenty hot enough. You could even have a very small flame like this. It looks good. All right, we don't know what contaminants are on our platinum wire. You know, so you should do this in the hood. Because if somebody were really testing their unknown contain lead, it can contain mercury, it could contain, you know, all kinds of poisonous ions. And if you introduce it into the flame, you're just going to vaporize those atoms into the air and then inhale them. And so you don't want to do that. You want to do all flame tests inside the hood. This one, let's just take a look at what it looks like. Do you see the flame color here? Yeah, it's yellow. That's sodium. Yellow-orange. Bright. And so, well, this means our platinum wire's dirty, or our DI water had a lot of sodium in there. And so before I test my sample, what I need to do is I need to clean this. Did I talk about cleaning the platinum wire before? Question? I'm sorry? Flame? No, it's not supposed to be. Somebody forgot to turn it off. Somebody was doing the flame test there. All right, this is what I recommend. I recommend that you skip the sodium test for now and do the sodium flame test after you do the magnesium flame test. The reason is because it takes a long time to clean the platinum wire. I mean, look how bright the yellow is there. And so you could sit here and try to burn off all the sodium off the platinum, but it's going to take a long time. And so what we do to try to speed things up is we get some concentrated hydrochloric acid into a little test tube, and then dip the platinum wire in the test tube, and then burn it in the flame. Well, with concentrated hydrochloric acid, you don't want to be doing that on the bench top. And plus, the potential for toxic ions like chromium, lead, mercury, etc. You don't want to be doing it on the bench top. So you're going to be burning this in the hood. All right, everybody's going to test positive for sodium because the first sample you're going to run contains all the species. And so rather than cleaning it and then testing your unknown, which contains sodium, and you'll get a nice positive test for sodium like this, and then having to spend another 30 minutes to clean it for magnesium, the easiest thing to do is clean it once, test for magnesium. Magnesium gives you a very faint brick red color. It doesn't last very long. And so after magnesium, it's very easy to clean the platinum for your sodium test. And then once you run your sodium test, then you're done with the flame test. Okay, this will save you one cleaning procedure. If your platinum wire is clean, you know, you can check it and see. My platinum wire is very dirty. This would take a long time to clean. Okay. I just skip it for now. But let's talk about the sodium test, and then we'll talk about the others in sequence. So what I'm going to do is for each ion, I'm going to write down the key observations and the key equations associated with it. And so for the sodium ion test, the key observation would be this. We take our unknown aqueous and then we introduce that into the flame. And then we get a yellow flame. This is a positive test for sodium. The equation that's going to be associated with this is that the unknown must contain sodium ions in solution. So we have sodium ion AQ. And then when we place this into the flame, a number of things happen. One, we vaporize the ions into the gas phase. And so we'll have sodium ions, gas. And then two, we look at the flame, you know, what's happening in the flame here. Oops. Right, the camera. So when you look at the flame like this, you know, there are different regions. Right on the cone, that's where we're getting the correct stoichiometric ratios of fuel to air, you know, methane to oxygen. Right? Inside the cone, like say in the middle of the cone, it's excess methane. Right? Outside the cone, we have the excess oxygen kind of region. And so we have different regions of the flame. We have the reducing region of the flame, which is the excess methane. We have the oxidizing region of the flame outside here, and then we have the stoichiometric region of the flame. You know, where's the most of the heat being produced? Well, most of the heat's being produced at the surface of the cone, where it's stoichiometric. And right at the tip of the cone is where you're going to get the hottest part of the flame. And that's where we typically use, because like down here in the middle, I mean, the match doesn't even ignite, but you know, right at the tip of the cone, it's good. And so inside the flame is a plasma, and the plasma is, you know, high energy gas. It's partially ionized. There are free electrons and ions in the gas. And so what happens in the flame are that the sodium ions are reduced to sodium metal. But those atoms of sodium metal will be in the gas phase. In this plasma, there are energetic collisions. And if the collision is energetic enough, then it'll excite the sodium atom. When sodium atoms get excited, what happens is an electron gets promoted. You know, an electron would get promoted from a 3s, its valence electron, from a 3s orbital to a higher energy orbital. And so this double dagger is just to indicate that an electron has been excited to a higher energy orbital. That electron doesn't stay in a high energy orbital indefinitely. It's going to drop back down to its ground state. When it drops back down to its ground state, that excess energy is released as a photon of light. And so the sodium here gets back down to its normal state in the gas phase, plus H nu. This turns out to be in the yellow region of the visible spectrum. So we get that. Sodium street lamps work the same way, except sodium street lamps will just take sodium solid and vaporize it, excite it, and then have it emit yellow photons. All right. The next species we're testing for will be ammonium. So let's take a look at the ammonium test. If our unknown contains ammonium ion, we can detect the presence of that species by, well, ammonium, what is that? Yeah, ammonium is a conjugate acid of ammonia, or ammonium is an acid, basically. So if it's an acid, we can react with a base. What we're going to do is we're going to add sodium hydroxide, and then we're going to heat it. We add sodium hydroxide and heat it. It's probably best done in a beaker, small beaker. What we're going to do is we're going to put a watch glass on top of this. We have a watch glass on top of this, and then we try to detect the presence of the gas. We're going to detect the presence of a gas by sticking a piece of red litmus. It's going to be wet. Red litmus on the bottom of the watch glass. And so if you just wet a piece of red litmus paper, stick it on the bottom of the watch glass, and then cover the beaker, we can let the gas, whatever gas is generated, come into contact. And so the gas that's generated will come into contact with the red litmus. And what will happen is that red litmus will gradually change to blue. So we get blue. And so we have to make sure that the gas and not the liquid comes into contact with the red litmus. That's very important because this liquid is going to contain sodium hydroxide. Sodium hydroxide is a powerful base. If that red litmus comes into contact with this solution, obviously it's going to turn blue. And so what we're trying to see is if the gas turns it, and it should be very homogeneous and to gradually change or fade from red to blue. And so the observations for this, we could write as one sequence, or we could separate it into steps. We take our unknown aqueous, and then I'm going to add some sodium hydroxide. And then what this does is, and heat it, what this does is it generates a clear colorless gas, a CCG. And then we expose this to red litmus, and then the CCG, the clear colorless gas, turns the litmus blue. All right, the equations that go with this are going to be, our unknown therefore contains ammonium ions. The ammonium ions will react with hydroxide ions. When ammonium reacts with hydroxide, we form ammonia and water. The problem is ammonia is very soluble in water, and so a lot of the ammonia will be aqueous, and some of it will be gas. Yeah. Normally we write NH3 gas plus H2O, ammonium hydroxide decomposes into ammonia gas and H2O, but you'll definitely smell it, but we don't get rid of all that ammonia. To get rid of all the ammonia out of solution, we have to heat it. And so that's going to drive the ammonia that's dissolved in the water out. And so we end up with NH3 gas. Like this. Now the NH3 gas is going to react with litmus. So I forgot to write this equation in the morning. But the equation for this looks like this. The litmus, red litmus, is like this. H lit. Red litmus is actually an acid, and it's going to react with the base ammonia in a Bronsted acid-base reaction. And so it's going to form ammonium plus LiT minus. LiT is just, it's an organic, so the anion is quite big. And so rather than writing it all out, we do an abbreviation like, OX for oxalate, LiT for litmus anion. And so this is blue litmus. This is all in the gas phase here. The litmus is in the aqueous phase. The ammonium will be in the aqueous phase, and this will be in the aqueous phase. So we'll have the ammonia gas coming out there. So these would be the reactions associated with the ammonia test. The next test is very long. Silver, you're not just testing for silver, but you're testing for all the remaining ions, all the remaining cations in one long sequence, 8 of them. Okay. These two tests, the sodium and the ammonium tests, they're just run separately. And so you're going to get a sample from the stockroom. It's called the known solution. The known solution contains all the species, and you're going to go through a trial run to make sure it's working, all the reactions are working, and you know what to expect or what they look like. And then after you run through the known, then you'll run through an unknown. While we're running through our known, what we have to do is we remove some of our known sample to test for sodium. The sodium test is so sensitive, you only need about 3 drops. You put 3 drops of unknown in the test tube, and then test that. You don't want to use your entire sample, right? Because for potential for contamination or whatnot. The same thing for ammonium. You only need how many drops for the ammonium test? 10 drops? Is that right? 8 drops? How many drops of unknown aqueous do we use for the ammonium test? 10 drops. And so we'll take 10 drops, separate it from the rest of the solution, and then just test that separate sample for ammonium. Okay, then do we use the rest for the silver and the remaining cations? No, we aren't going to use all of it. We'll use most of it. How much do we use in the silver test? 10 drops? 10 drops, we just used 10 drops for the ammonium test. Now we're going to use 10 drops to test for all the remaining ions, all 8, is that 8? All 8 of the remaining ions? What do you think? Just 10 drops? Is that going to be enough? Here's where we're going to make an adjustment to make your life a little bit easier. 10 drops isn't so much. I'd probably use more than 10 drops. Like 15 drops. 15 drops would be better. And then the procedure says to add 10 drops of the unknown plus 5 drops of water. Why do you want to add water? Because if you add water, it makes things more dilute, which makes things harder to detect. And so there's no reason to add the water unless there's a specific purpose. But there's no specific purpose here. And so rather than adding 10 drops of unknown/known and 5 drops of water, just use 15 drops of unknown. But if we use 15 drops, we're using 50% more. Does that mean we have to use 50% more of everything else? Maybe not. The way we do this lab is those numbers, like 2 drops, 4 drops, 3 drops, those are just guesstimates. What you have to do is you have to adjust those as you're doing the procedure. Otherwise, if you don't make adjustments, you're going to get very bizarre results. And so let's talk about how to make those adjustments and what we're after. And so what we're going to do is we're going to test the remaining unknown for all the remaining ions, but not all. I don't know how much unknown they're going to give you from the stockroom. And so we're going to get 15 drops of unknown, quote unquote. We already know that our unknown contains everything. You can work with a partner for this, but make sure each of you knows what's going on. That is, don't let your partner do all the work, because one of the questions I don't like, but I get every semester, is that, during the unknown, you can't work with a partner. During the unknown, you can't even open your lab manual. All you have is your lab notebook and the observations that you wrote. And so this question I get asked every semester, where can I find this chemical? And this should be the second run through. And so I asked them, didn't you do it before? And the typical answer is, no, my partner did it. My partner got that chemical, so I don't know where it is. And so that's not, I'm not going to tell you where it is. You're going to have to figure that out. And other things, like, for example, where can I find the 16 molar? There's only 15 molar here. What should I do? Well, then I asked them, what did you do during the known analysis? Well, they didn't do that step. And so to prevent this type of stuff from happening, you should be very involved, with your partner and in the analysis, so that you know exactly what's going on. And so here, we take 15 drops, and then what do we do? Well, in the silver analysis, this contains silver ions plus a bunch of other ions. And so what we have to do is we have to separate all those other ions from silver, or we have to separate silver from all the other ions. And so what we're going to do is we're going to separate silver. We look for something that only reacts with the silver ion present, but not the other species, and that would be HCl. In the procedure, it says to add 2 drops of HCl, but 2 drops might be too much, or 2 drops might not be enough. How do we know? Well, it depends on what we're trying to do in this particular step. In this particular step, we're trying to separate out the silver from everything else. And so I'm using dash for solutions. So this would be our unknown. And I'm going to just do this in flowchart format. The HCl should react with the silver ions to precipitate out AgCl, like this. Unfortunately, chloride doesn't just react with silver ions, it also reacts with what else? Lead and mercury. So it's possible we get some PbCl2 and some Hg2Cl2 here. Those would also precipitate out with chloride. But we're going to separate that from everything else. Everything else should just stay in solution. And so it's critical that we do these separation steps properly. And so we're trying to separate out the silver, which means we have to precipitate out all the silver, all of it. So let's say we add 2 drops and you get some white PPT, and then you stop there. Well, the problem with that is that you might not have gotten all the silver out. Some of the silver, if you didn't precipitate all of it, will end up here with the other ions. If silver ion ends up over here with the other ions, then that's what we call an interference or potential interference. And what that does is it screws up the other reactions we're going to do later. And so we don't want any silver over here. We want to make sure we got all the silver out over here. 2 drops may or may not be enough. Instead, and this is something they didn't do, instead we should do something like we did for barium sulfate. What did we do for barium sulfate to make sure it all precipitated out? Do you guys remember the barium sulfate precipitation in Chem 1A? You tested it to see if you got additional precipitation. And so what we do is, okay, 2 drops, it precipitates. A 3rd drop, it continues to precipitate. A 4th drop, it continues to precipitate. When should I stop? When I stop is when it stops precipitating. And so what I need to do is I need to maximize the amount of precipitate. If I continue adding, sometimes this happens. I maximize the amount of precipitate and then the precipitate starts to disappear because some other side reaction occurs. And so you have to keep a close eye. We just want to maximize the amount of precipitate and then stop there. The problem is that silver chloride turns into a cloudy white solution. And this cloudy white solution, each time you add a drop, it's impossible to tell. It's like, you know, you're in this thick fog and you can't see. You can't see if it's getting foggier or less or not because you can't see anything. And so what we can do here to help us see if we get additional precipitation or not is use a centrifuge. This way we can speed things up, because in the barium sulfate what you had to do was you had to wait for the precipitate to settle to the bottom of the beaker, and then you tested the solution above that. You remember that? Waiting for it to settle sometimes took some time. We don't have time to waste. And so for this, what we're going to do is we're going to just force the precipitate to the bottom of the test tube. We can force the precipitate to the bottom of the test tube by centrifuging it. And so let's say I have my cloudy white precipitate here. I can't see anything. I want to test it to see if I get more precipitate. And so what you're going to do is you're going to get a counter test tube. We have 3 different sizes of test tubes. You know, we have these mini ones, the baby ones, medium ones, and the large ones. The centrifuges can accommodate all 3 sizes, but you have to be careful about which insert you use. You know, the blue ones are for the baby. These white ones are for the medium size. You see the, and then we just remove the insert, for the large ones. So I have 2 medium-sized ones. I'll just put them in the white insert here. You want to put them on opposite sides to counterbalance this. And so this is what it should sound like. There's a little knob here to twist to turn it on. So I turn it on, and then I just listen to it. When it hits maximum speed, just turn it off. We just need to ramp it up to max speed and then click it off. That should be adequate. And then what we'll do is we'll get a piece of paper towel, like this. And then we're going to break the centrifuge to slow it down, otherwise it takes a long time to slow down. So just gently break it. You don't want to bring it to an abrupt stop, because if you bring it to an abrupt stop, you'll dislodge the precipitate and have to recentrifuge it. But if you bring it to a slow, gradual stop, the precipitate should be nicely coagulated at the bottom of the test tube. Okay, if the precipitate's coagulated at the bottom, then you should have a clear solution above, and then add a drop of HCl. If you get more precipitate, you just got to keep adding until when you add a drop, it stays clear. no precipitate happens. Then you know you got all of it. And so what we need to do is we need to make sure all the silver ends up over here. None of it ends up here. Okay, the next thing we have to do is we have to separate the precipitate. You know, we'll centrifuge it again, so the precipitate should be stuck at the bottom. How do I separate the solution from the precipitate? The solution we call the decantate or the supernatant. Well, we just decant it. You know, decanting is just to pour it from one test tube to another. But sometimes what happens is a little bit of precipitate gets stuck on the surface of the water of the solution, and it's too hard. There's too much surface tension to break the surface. So you can try centrifuging again and again, but it just doesn't settle to the bottom. And so an alternative is to get one of these plastic pipettes and then suck the solution from the middle, you know, not from the top, not from the bottom, and then transfer it that way. Right. Are we going to be able to get all the decantate? No. You know, some of the crystals are going to be wet with decantate. And so what should I do? Well, that's a problem. It's a problem because, one, the decantate is going to contain all the other ions. If it contains all the other ions, then it's going to screw up these tests. You know, it's going to make all the colors weird, and we're going to get side reactions occur, and other problems. So we don't want any decantate contaminating our crystals. And since we didn't transfer it all over, what we're going to do is we're going to wash the crystals. And so what does it say about washing the precipitate? It says to use, well, we're just going to wash with water. It says to use 10 drops of water. And so we're going to use 10 drops of water, but we don't discard that wash. Do you know what we do with that wash? We pour it in with this decantate, because that wash is going to contain some of these ions, and if we lose that, then it's going to make things harder to detect down the road because we're going to have a lower concentration. And so we don't want to lose anything. And so what I want to do here is I want to alter the wash procedure. You know, rather than doing one wash with 10 drops, I recommend doing, this is what I would recommend. I would recommend doing 3 washes with 5 drops. And so you do a wash with 5 drops. That rinse water is going to be highly contaminated with decantate ions. And so the first wash, we're going to combine with the decantate, not to lose any. Okay, then we're going to do a second wash. You know, when you wash this, you get your stir rod, you mix up the crystals, then you centrifuge it. We're going to do a second wash with 5 drops. In the second wash, pour it in with the decantate. Then we're going to do a third wash with 5 drops. The third wash with 5 drops should be pretty clean, the rinse water. And so what we're going to do with the third wash is just dump it into waste. Okay, what that's going to do is it's going to make sure our precipitate doesn't have any contaminating ions on the surface of it, and that we've recovered most of the decantate ions over here, or the supernatant ions over here. Is that clear for everybody? All right, good. So we get a white precipitate. It could be silver chloride, lead, or mercury chlorides. They all look white. And so what we're going to do is we're going to do some subsequent tests. You know, we want to do something that only reacts with silver chloride, but not the lead and the mercury. And so do you know what that test is? So we have some clean precipitate here. We're going to test the precipitate with ammonia. And what that does is ammonia reacts with the silver chloride, which is, these are all solids, but not the lead and the mercury. And so the silver chloride precipitate actually dissolves to form the diamine silver ion. This is chloride. We have the simple version of qualitative analysis. In normal qualitative analysis, we would dissolve all the silver chloride, leaving us with a precipitate of these, and then separate. But are we going to have lead and mercury as one of the possible unknown cations? No, actually there's no lead and no mercury here. And so we're just kind of going through the motions. This is what we'll do, if we had them. One thing you have to be careful with is don't throw away anything. Now, even though we're on the silver branch, we still need the decantate for subsequent tests. And so, unless you're absolutely certain we aren't going to need it, don't throw precipitates and don't throw solutions away. All right. Once we dissolve that, how much ammonia did it say to add? Here? Four drops. Here we ignored that completely. What are we trying to do in this step? Dissolve the precipitate. We don't have any lead, we don't have any mercury. So let's say the precipitate dissolves with 1 drop. If the precipitate dissolves in 1 drop, should you add the remaining 3 drops? No, because if you add the remaining 3 drops, then it screws up the subsequent test because you have way too much excess ammonia, right? And so just add the amount that is required to do what you need it to do. Some people, they add 4 drops. They add 4 drops and they sit there with a stir rod crushing the crystals, but they didn't all dissolve. What should they do? Should they stop there because it just said to add 4 drops? No, they have to keep adding. It doesn't matter how many drops it takes. The purpose of this step is to dissolve all the white PBT. And so if it takes 15 drops, then go ahead and add 15 drops, 20 drops, whatever it takes. You have to get all the precipitate to dissolve. All right. Once we get all the precipitate to dissolve, with the right amount of ammonia, we're going to add nitric acid to this. What the nitric acid is going to do is it's going to reform the precipitate. And so how many drops of nitric? I got asked this question this morning. How many drops of nitric are required? Until the litmus turns acidic. And so what we need to do is we need to add enough nitric acid to kill off any extra ammonia that we have and then make it acidic. If we make it acidic, well, should I take some blue litmus and then dip it into the test tube? Now, when you test with litmus, what you have to do is you dip the stir rod in the solution and then put a drop of solution on the litmus paper. See what color it is. Well, some people turned their litmus blue, but they didn't get any precipitate. So they got their, actually blue, they don't want it blue, they got it red. So they turned it red and didn't get any precipitate. What would you tell them? Add more nitric acid, right? Add more. Add more until you see what? What should happen? A white precipitate. And so, you know what? I wouldn't even bother. Do you really need to, do you really need litmus? No, what we're trying to do is we're trying to regenerate a precipitate, and you could save yourself time because why bother even testing it? Just keep adding the nitric until the precipitate reforms. You saved yourself a couple of minutes. Right? All right, so this is the test for and sometimes it's easier to understand how we can modify the procedure if we see, the reactions that are occurring. And so let's go through the silver test in terms of the key observations, actually all the key observations and the equations. And so in step 1, I'm going to call this step 1 here. The observation is we take our unknown, aqueous, and we add HCl to this. We get a white PPT. And so the reaction that's occurring here is that our unknown must contain silver ions, and these silver ions will react with the chloride ions from HCl to form AgCl solid. This is a metathesis reaction. 2, we take our white PPT from step 1, or I don't have to say white, I just say, let's take our PPT from step 1, and then what are we adding to it? Ammonia. And then we get a CCS. CCS stands for clear colorless solution. So the precipitate dissolves to form a solution. And so the reaction, or the equation for that, is that we have silver chloride solid, and then the ammonias attack it as a Lewis base. And these are going to form the diamine silver ion plus chloride, AQ. And so our precipitate dissolves. This reaction we're going to see in chapter 18. This is just a Lewis acid-base reaction. Okay, 3, we're going to reform that precipitate by adding nitric acid. And so in 3, I'll write it up here. We're taking the solution from 2 and adding nitric acid to it, and we get a white PPT. All right, for the observation, the equation we can do in 2 ways for this. One of the equations I'm going to write is backwards. And so this is the equation here, 2 ammonias, the diamine complex plus chloride. And what I'm going to do with this equation is Le Chatelier's principle. Le Chatelier's principle says, when we have a system at equilibrium, let's say we add a lot of ammonia to this, and so we add a lot of ammonia, we're dissolving all the precipitate, we get the diamine. Then we can think of this as being balanced, but we can knock things out of balance. So for example, one way we can knock things out of balance is remove product or remove reactant or add, add product or add reactant. And so if I say, this is reactant, this is product, and this is water well here, if I remove reactant out of here, let's say I suck water out of this side, then the net flow of water will be backwards here. And so this is what I'm going to do. I'm going to suck this reactant out of here, and then have this flow backwards. The way I suck this reactant out of here is by killing it with nitric acid. In other words, ammonia will be attacked by nitric acid, and when ammonia gets attacked by nitric acid, we're going to form ammonium nitrate. And so what we're doing here is we're removing this, and what that's going to do is it's going to shift this backwards. We call it shift left in Le Chatelier's jargon. And so we have this system that's at equilibrium, it's balanced. It's biased towards the product because we've just dissolved all this. But since it's a two-way reaction, we can reverse this by removing some reactant, the ammonia in this case, and replacing it with ammonium. And so this is just Le Chatelier's type. The other way we can represent this is just like this. And so I'll just say, or, we have our not silver chloride, we have our diamine silver ion plus chloride plus nitric acid. Nitric acid, nitrate's a spectator. So it's just the H+, the same thing. I could have just written H+ here, because nitrate's a spectator. So if I wrote H+, then it's just going to go to ammonium ions. Ammonium nitrate's a strong electrolyte, so it's split apart anyway. And so over here, I'm not going to worry about the nitrate. This is H+ from nitric acid. The H+ is going to attack the ammonia that's attached to silver. When that happens, it'll convert it from ammonia to ammonium. And so we end up with silver chloride solid back and ammonium ions here. we're going to need 2 H pluses to balance. We'll end up with 2 ammoniums over here. There are other, when we get to chapter 18, we're going to break this down into little steps. And when we break this down into little steps, it's easier to see, because what we're doing here is we're just writing the net reaction here. But these are the 2 ways you can represent the formation of silver chloride, or the regeneration of that precipitate. And so we just keep adding the nitric acid, add more and more nitric acid until you get the desired product. And so really there's no reason to test it with litmus at all, because if you overshoot with nitric, you know, well, everything's shifting this way. So if you overshoot with nitric, then you're going to eliminate all the ammonia. Well, that's no problem, because we want silver chloride. Okay, this series of reactions means that, yeah, we can be pretty confident that we have silver ions present based on the reactions and properties, physical properties that we tested with. Okay, so we're done with that branch of the flow chart. Now we got to go back to the decantate and then see what are we doing with that solution that we had from earlier. And so this is going to contain this from the other branch. All the remaining ions. So we have what? Iron, aluminum, chromium, etc. Right. So what's the next step here? We just finished adding HCl. Now we're going to add ammonia. Yeah. So we add ammonia. Well, there's excess HCl present, and so the HCl is going to attack the ammonia. But we want to continue adding ammonia, because what we're trying to do here is we're going to try to precipitate out the hydroxides. And ammonia is a hydroxide precipitating agent. In fact, we want to do this. We want to precipitate out the +3 cations, but leave the +2 in solution and the +1 in solution. And the way we can do that is by controlling how much hydroxide we put in solution. How can we control the amount of hydroxide we put in solution? Well, it depends on how much ammonia. The more ammonia, the more hydroxide. And so we don't add too much hydroxide because of this. If we add just the right amount of ammonia, what's more soluble, what's less soluble? You know, +3. Are +3 hydroxides, like iron 3 hydroxide, more or less soluble than a +2 hydroxide, like iron 2 hydroxide? The +3 are less soluble. And so the +3, being a lot less soluble, are much more sensitive to hydroxide. We just need a tiny bit of hydroxide, and these +3s will precipitate out. But if we add too much hydroxide, you know what's going to happen? Too much hydroxide will begin to precipitate out the +2. And so we have to be careful. You know, we have to add enough +3 so that all the +3s precipitate out as completely as possible, but not add too much, because if we add too much, then the +2s start to precipitate out, and that's going to screw things up. And so rather than using something like sodium hydroxide, you know, would introduce a much larger quantity of hydroxide to this. And so sodium hydroxide would precipitate out the +3 and the +2s. Ammonia can precipitate out +2s as well, but you need a lot of ammonia to precipitate out the +2s. So we're just going to give it a little bit. And so right now the solution's acidic. Now we need to use litmus paper. Litmus paper is very important here, because litmus paper is going to tell us, you know, when we've gotten rid of all the acid, the excess HCl. And so we're going to test it. Right now it should be acidic, the red litmus should be red. But we're going to add ammonia until it becomes neutral. It's going to become neutral when it just starts to turn red litmus to blue. And so we got to get red litmus to go blue here. And then it should start to precipitate out. Well, the red litmus goes blue, and then we add what? Ammonium chloride. Ammonium is an acid. And so what we're doing is this. On the pH scale, we're making it more and more basic, and then we hit about neutral. And then we add a little bit of ammonium to bring it down slightly. Okay, this is just to control how much hydroxide. And so if we don't get too much hydroxide, then we expect 3 precipitates. Iron 3 hydroxide, aluminum hydroxide, and chromium 3 hydroxide. The magnesium ion, etc., should stay in solution. And so over here we'll have the solution of others. In this case, we aren't going to maximize it. We aren't just going to keep adding the ammonia, because if we keep adding the ammonia, we're going to get the magnesium to precipitate here and other things and make a mess. And so what's the best way to maximize the amount of precipitate here? Well, the best way is, you know, it turns out magnesium hydroxide doesn't precipitate until we get to pHs of 8 or 9, which is very high. And so we have a little bit more flexibility than what they're giving us here, because they want us to get it just to neutral and then make it slightly acidic by adding the ammonium. What we can do is we can get it slightly basic. We don't want the litmus to turn a dark blue, but light blue is still okay. And so if you aren't getting any precipitate, some people weren't getting any precipitate when it hit neutral. If you aren't getting any precipitate when it hits neutral, should you add the ammonium then? No. What should you do? You should add more ammonia, generate more. And so you don't have to worry, unless you go crazy and add way too much ammonia, then you'll start to precipitate out the other ions that will interfere. But we still need litmus, because, you know, if we don't use any litmus, then we can go a little bit too crazy on the ammonia and precipitate out way too much, you know, of the other ions. All right, now we have a mix of 3 precipitates. Do you know the colors of these? This is rust colored, yeah. Yeah, colorless or white. And this is gray-green. So we got a mix of precipitates here, different colors. We can identify based on colors, but sometimes it's difficult because you get a mix of colors, so it's hard to tell. So what we're going to do is we're going to separate, you know, one of these from the others. So we got to figure out which one we can separate, or which 2 we might be able to separate. Well, what we're going to add next to this is sodium hydroxide. Do you know what the sodium hydroxide does? Sodium hydroxide, does it react with the iron? Does it react with aluminum? Yeah, it reacts with aluminum. And it doesn't react with the chromium. But you think aluminum's already got 3 hydroxides, that's all it wants. No, aluminum hydroxide can be attacked by another hydroxide and form this. What is this called? Tetrahydroxoaluminate, and that's aqueous. And so what we do is we dissolve the precipitate. So the purpose of this step is we're going to add sodium hydroxide to make sure we dissolve all the white precipitate. But will the sodium hydroxide react with the rust or the gray-green precipitate? That is, will the sodium hydroxide form tetrahydroxoferrate? or tetrahydroxochromate? Why not? Why not? I mean, this is what we call Lewis acid-base reaction. Hydroxide is a good Lewis base. Those must be Lewis acids there. So why doesn't the tetrahydroxoferrate, and why doesn't the tetrahydroxochromate form like the tetrahydroxoaluminate? I'm sorry. Well, the aluminum did too. I mean, all they need are the 3 hydroxides because they're all 3+ cations. And so the question is hydroxide a good base? Yes. It attacked the aluminum, it formed the tetrahydroxoaluminate, 3. Why didn't it attack the iron and chromium? This is just a review question. This is a review question because for Bronsted acid-base reactions, it's very simple. Any strong acid will react with any base, basically. Well, we got a base here. Why doesn't it react with any acid? And the answer I'm looking for is that Lewis acid-base reactions are pretty easy to predict or pretty complicated to predict? They're complicated. Why are they complicated to predict? Well, there are no rules because, well, there are rules, but the rules we didn't get into because the rules were too difficult for us. Or not too difficult, they were just beyond the scope of the class. We didn't have time to get into the rules. And the rules, what governs, what Lewis acid reacts with what Lewis base? It has to do with bond formation. And the electron pore stuff, we can use that, but primarily it's bond formation. In order to predict bond formation, or in order to understand bond formation well, you need to understand what theory very well. Yeah, molecular orbital theory, and you need to understand what makes a good LCAO. What makes a good LCAO? Do you guys remember LCAO? What's that acronym stand for? LCAO. Nobody? Actually, this is way back to week 1. Week 1 when we're talking about Lewis acid-base reactions. It was on the PowerPoint. LCAO stands for linear combination of atomic orbitals. When you do molecular orbital theory, you have to do linear combinations of atomic orbitals. And so what makes a good LCAO? Usually soft plus soft or hard plus hard. Does that ring a bell? Soft, hard, soft, acid-base theory we could use to try to simplify. They're trying to simplify things to say what makes a good linear combination of atomic orbitals. Because linear combination of atomic orbitals is what makes molecular orbitals. And so, well, how many of you guys are well versed in quantum mechanics? Probably nobody. And so this is why Why don't these form? The answer might be, I don't know. I don't know why those don't form. I mean, that's just what's observed, And then you might speculate it must have something to do with the bonding and the orbitals and all that molecular orbital stuff that's beyond us. And so what we do here is, this isn't simple like Bronsted. What we do when we're looking for Lewis acid-base reactions is we go to a table or a book and we see, does it do that or does it not do that? And so what we could do is we look in Appendix D. Does it form a hydroxo complex? Iron does not. Chromium does not. aluminum does. And we just do it based on observation. And so you aren't going to be predicting those. And there's a reason. That's the reason. And so anyway, we need to add enough hydroxide to do this. And so how many drops of hydroxide does it say to add? 10 drops. Is 10 drops enough? Probably, but just keep an eye on the white PBT, right? That's what you're trying to do. Trying to dissolve all of it. All right, so we dissolved all the white precipitate with however many drops of sodium hydroxide it takes, and then what are we going to do? We're going to add acid. Here you don't want to add too many drops of sodium hydroxide, otherwise you're going to have to add too many drops of acid to neutralize all that. What acid are we adding? We're going to add HCl. And what that's going to do is it's going to destroy the complex and form aluminum. And so, in other words, we'll just get aluminum ions here. And then what are we going to do? And then we add ammonia to reprecipitate. And then what do we do? And then we add HCl again. And then we'll end up with aluminum 3+. And then what do we do? We add aluminum and ammonia. And we should get what? Okay, red precipitate. Okay, the red precipitate is going to be what we call a gelatinous precipitate. Was the aluminum first or was the iron first? Iron was first? Okay, this is why I didn't talk about it in the morning. But it's okay, since we followed the aluminum branch, we'll just finish off with aluminum here. Even though we should have done, I guess we should have done the iron. Let's see. Should we do the iron? Let's do the iron since we're supposed to do. The chromate's all the same, but I'm not going to finish. I'm just going to finish the iron, and then we'll look at how we separate the chromium. Because at this particular step, we're adding both sodium hydroxide and what else? When we add the sodium hydroxide to this, what we're going to get is this. We're going to have our iron 3 hydroxide and chromium 3 hydroxide untouched. So those aren't going to react. And then, to separate the iron from the chromium, we add hydrogen peroxide, some heat. What does the hydrogen peroxide do? Yeah, hydrogen peroxide oxidizes the chromium. So hydrogen peroxide is an oxidizing agent, and the chromium is going to be oxidized to chromate or dichromate. CrO4 2-. And so we're going to oxidize the chromium 3 hydroxide to chromate, which is going to be aqueous. Chromate and dichromate are interesting because when we look at the oxidation states, you look at chromate versus dichromate, chromium is +6 in both of these. And so we're going from chromium +3 to chromium +6. Well, if both of these have chromium +6, why does chromate form and not dichromate? So this is important. Chromate is yellow, dichromate is orange. And which one of these forms depends on pH. So for example, if you take dichromate, this orange one, and make it more acidic, that is, you add acid to this, then what happens is the dichromate gets converted to two chromates. And so this is kind of Le Chatelier's principle. The more acid we have, that is, the lower the pH, the more yellow this solution is because we have more chromate. The more basic this is we remove the H plus by adding hydroxide. The more basic this is, then the more orange this solution will be. And so in order to get a yellow color here, this solution has to be acidic, which it is. We'll test this further, but let's take a look at the iron, because the iron, we aren't oxidizing. Could we oxidize iron from +3 to +6? No. And so iron hydroxide will be untouched. Now the iron 3 hydroxide, what are we going to do to that? We're going to add HCl. Okay, that's going to destroy our precipitate and form iron 3 plus in solution, plus other stuff. It's not balanced. And so we dissolve our precipitate in HCl, and then what do we do? Potassium. K4FeCN6, which is called potassium hexacyanoferrate. What's the charge on iron? Ferrate 2 is correct. When we add that to iron 3, then we form a precipitate. And so this whole ion is 4 minus. This is a 3 plus. So we're going to get Fe4, FeCN6, 3, solid. This precipitate, even though it has cyanide, the cyanides are locked in the complex. So it's not especially toxic. In fact, this precipitate is called Prussian blue, and they use it to dye things like blue jeans or whatever else. And so this is a blue precipitate. All right, since you're testing iron next, let me go through the observations and equations for iron, and then I'll write the ones for aluminum and chromium next time. Again, each of these separation steps, you want to make sure they're complete and that you wash any precipitates thoroughly using the wash procedure we talked about. But the test for iron, we start from the beginning. So this is the test for iron 3 ion in solution. So we start off with our original unknown aqueous, and then we add HCl. And iron doesn't react with HCl. And so the equation for this is iron 3 plus HCl yields NR. There'd be no reaction here. This is the first step. In the second step, we added ammonia. And so we'll take the solution from step 1 plus ammonia. Well, when we add ammonia to this, we get a precipitate. This is a rust-colored precipitate, although it might not be so visible like this. All right, maybe this is So the reaction for this is iron 3 plus 3 ammonias plus 3 waters yields iron 3 hydroxide solid plus 3 ammoniums. So we precipitate out the iron with ammonia. And then in the next step, we took the precipitate from step 2 and then added sodium hydroxide to this. I'm not using, we got NR. And so that means the iron 3 hydroxide here, solid, plus the sodium hydroxide yields no reaction. And then in the next step, we took the precipitate from 3 and then added the hydrogen peroxide to this. And so that precipitate showed no reaction. And that is, iron 3 is already pretty much oxidized. We aren't going to oxidize it more, hydrogen peroxide. We got no reaction here. And then in the next step, we took our precipitate from step 4 and then added HCl to it. Okay. And then we got a solution. This would be a clear kind of yellow solution, or it might be close to a CCS. You know, the color is going to be very faint here. And so the reaction here for that is we took our iron 3 hydroxide solid plus, I'll just do it in net ionic form, 3 H pluses. This is going to give us iron 3 plus 3 water liquids. And then we took our solution from step 5 and then added the potassium hexacyanoferrate 2. And then we got a blue precipitate. And so the reaction here is that we're going to take 4 iron 3 pluses and 3 hexacyanoferrate 2s. This is a 4 minus. And then we end up with Fe4, FeCN6, 3, solid. So that would be the iron analysis. After we've gone through all these steps, then we say we have a positive test for iron 3 plus solution. All right, next time we'll look at aluminum and chromium and some of the others. So I'm going to stop here and then you can start. Let me just tell you a couple of things. You'll check out a platinum wire from the stockroom. You're going to keep this for the entire semester, but platinum is very expensive. Do you know how much this? I think this is like $200 worth of platinum or something. So be careful with this. If you don't feel comfortable storing it in your drawer, you can just return it if you want. But make sure your drawer is locked so nobody gets in there, takes it. Maybe I should say it's not worth that much. Maybe I should say it's like nichrome wire. But if you lose it, it's going to be very expensive to build. The other thing is, oh no, Brooke. It's a Pyrex, so be careful. The other thing is again, the known part you're going to be working with a partner, but when it comes to the unknown, you have to do it by yourself. Okay, close the lab manual, just from your notes. So make sure you take good observations so that you can repeat everything when the time comes. Okay. All right, that's it. Go ahead and get started.